Hi, my name is Brianna Poon, and this is my report for Lab 2, Magnetic Field of a Bar Magnet. So the purpose of this lab is to use a magnetometer and a bar magnet to determine the distance dependence of the bar magnet. And so some fundamental principles I used were the Biot law, which allows you to calculate the magnetic field of a moving point charge. And then some other concepts that were important are that the magnitude of the magnetic field of a bar magnet is distance dependent, as shown by this equation over here, and also the idea that bar magnets are magnetic dipoles and can be calculated. The magnetic field can be calculated through these two formulas, the on-axis formula and the perp-axis formula, which are similar to those of the electric field dipole formulas. And over here, I have the equation for the magnetic dipole moment, which points from the south pole of the magnet to the north pole. So the procedure I use here was to first calibrate the magnetometer using a bar magnet, ruler, and tape, shown by this little diagram here, and then use that to measure the magnetic field of a bar magnet at different distances and use that data to calculate the distance dependence. And then I also created a computational model using the on and off axis magnetic field formulas derived from the Biot law. And then I compared my experimental data to my expected data to see how accurate I was. So some assumptions here are that the Earth still exerts its own magnetic field on the magnetometer, which must be accounted for, and also that the bar magnet can be treated as a magnetic dipole. And my model, in this case, the system is my phone or the magnetometer, whichever one. I use my phone as a magnetometer. And then also the surroundings are the magnet and the Earth. So here's an overview of my data. I measured the distances over here on the left, and this resulted in a plot of ln bx versus ln r, and this gives me the line of best fit formula, and I use this value, equation, to then calculate the dipole moment on the next page. So this first equation here is taken from my introduction page. If you take the natural log of this, you get this underlying equation here, which I compared to my line of best fit to calculate the value of k and also n, and r was my average distances that I calculated from my Excel sheet. And then using all of that, I set this equation equal to the on-axis magnetic dipole formula and solve for mu, and this is the value that I got. So some observations I made, when the magnetometer is far away from the magnet, it does measure a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field does not decrease, it increases. And the position of the magnetometer does have an effect on the measured x component of the magnetic field. And so using my calculated value for the dipole moment, I was able to create a computational model. So I plugged that value in over here and then wrote a function to calculate the magnetic field. And that is based on this formula, this general formula for the magnetic field down at the corner below. And on the right here is where I actually plot the arrows, and that's continued on the left. And then at the very end, I plotted an arrow at 45 degrees and use that to calculate the computational value of Bmag. And here's where I compared the two values. My experimental value was higher than my computational model value. So some errors that I may have encountered are like inaccurate calculation of the dipole moment, which could have affected my entire computational model since that value is based on my dipole moment value. And also I may have some errors with my magnetometer app, or it could have been influenced by other magnetic fields in the area, like from electronics. So if my experimental setup did not compensate for magnetic north, both the x and y components would be different since magnetic north is still contributing to the magnetic field measurements. And at an intermediate angle, magnetic north would contribute evenly to both the x and y components, and the z component would not be affected since the magnetometer is on a flat surface. And if I redid the experiment, but instead of using a single magnet, I used two identical magnets stuck together end to end, The results would still be the same because the magnets would still be pointing in the same direction. Um, but however, there would be a different magnitude. So the new result would pretty much be equivalent to replacing that 1 bar magnet by a stronger magnet that is like twice as strong as the original magnet. So that's the end of my report. Thanks for listening.